Okay, let's start to work on the problem one first. So in here we have a spring balance that is calibrated in an environment at 20 centigrades. So problem one, we have problem one. Let's work first on problem one. So the first case, when it is in 20 centigrade, we have 4 points of data over there. Right? So let's put the horizontal axis is the load, the vertical axis is the deflection. So the load, we have 4 points, a 0, 1, 2, 3, and then the deflection is 0, 20, 40, 20, 40, 60. Okay, so we have this point. Sorry, it might not be so proportional. I will plot it again. So it's like this. Okay, and then we need to first identify the sensitivity. We need to identify the sensitivity at 20°C first. So this is definitely, it will be a straight line, right, with the gradient of 20 millimeter per kilogram. This is for the case of 20 centigrade. Okay, the gradient here, of course, this corresponds to the sensitivity. Let's call it K at 20°C. Okay, now the second case, when the spring is calibrated in 30 centigrade, then the data is slightly different. I will plot it at the same graph, probably, to make it nicer. So when the load is 0, so I plot it in black. Black is the one in 30° here. Okay, so black is 30°. When the load is 0, the deflection is 5 millimeter. When the load is 1 kilogram, the deflection is 27. So 27 probably somewhere here. Sorry, somewhere here. When it is 2 kilograms, the deflection is 49. 49 is probably almost 50. And the last one is 71. Okay. So to this case, we take a regression also. The difference is about 22 for each of them. So it's like this. So the slope here, the gradient for 30 centigrade, the sensitivity, then it will be 22 millimeter per kilogram, where the equation of this, the linear equation of this, then it will be 22, let's say the mass is load plus 5, right? Well, for this one, the equation, the linear equation, will be just simply 22 times the load. Okay, So from here we can define all of the measurement parameter, the sensitivity of the spring in the environment of 20 degrees Celsius. Temperature is 22 millimeter per kilogram. When the temperature is 30 centigrade, then the sensitivity will be 22 millimeter per kilogram. And then from there we can also identify for this case that we have a bias equal to 5. So this is bias, and for this two calibration from 20 degree to 30 degrees Celsius, there is a drift of the sensitivity from 22 millimeter per kilogram to from 20 to 22. So there will be a sensitivity drift of about 2 millimeter per kilogram. And then the next one, what we can identify from here, definitely there is a zero drift here. So there is a zero drift from 20 degree to 30 degrees Celsius. Initially the zero is at 0, the A is 0 at 20 degrees Celsius. So there is a zero drift from 0 to 5. That means there is a zero drift. The zero drift rate is 5 millimeter per 10 degrees Celsius, which means this will be 0.5 millimeter per degree Celsius. There is the zero drift rate per centigrade. Okay, and then the next one, there is also a sensitivity drift, right? We know that there is a sensitivity drift of 2 millimeter per kilogram, but then of course we can also calculate the sensitivity drift rate in terms of centigrade. So the sensitivity drift, as you know, it's 2 millimeter per kilogram, but this happens for 10 centigrade from 20 degree to 30 degree per 10 degrees Celsius. So the sensitivity drift rate, then it will be equal to 0.2 millimeter per kilogram degree Celsius. Okay, so that will be the solution for problem 1.